Previously in the series on Laplace transforms, we've studied the Laplace transform of a derivative and the Laplace transform of the integral from 0 up to t of some function f of tau d tau. In this video, we're going to reverse the process. Instead of taking the Laplace transform of a derivative or of an integral, we're going to take the derivative or the integral of a Laplace transform. So our goals are going to be, first, take derivatives of Laplace transforms, second, take integrals of Laplace transforms, and thirdly, we're going to do a whole bunch of examples. In particular, we're going to look at a very famous differential equation called the Bessel equation. Let me begin with the definition of the Laplace transform. Here I have big F of s, which is the Laplace transform of little f of t and is defined by this particular improper integral. Now, what I want to try doing is taking the derivative of this with respect to s on both sides. So on the left, I just get f prime, but on the right, well, this is an integral with respect to t. So the derivative with respect to s can just come to the inside of the integral. In fact, the only spot where s appears is in the exponential. So if I bring that dds in, what it does is take the derivative of that exponential e to the minus st, and that just brings out a factor of minus t. But then looking at this integral that I get, that just looks like the Laplace transform of, well, the function minus t f of t. Indeed, it takes that minus t f of t, it multiplies it by that negative exponential, and takes it some proper integral. That was the definition of the Laplace transform. That is, the derivative of the Laplace transform, the derivative of capital F, is not related to the derivative of the original function, the lowercase f. Instead, it's the original function, but multiplied by negative t. If I take this derivative n times, every time you take a derivative, you multiply out by another factor of minus t. And so if you take n derivatives, you get the final formula, which is that it is a minus 1 to the n if you've taken the derivative n times. And then it's the Laplace transform just of t to the n times f of t. Let's see a couple examples of this. The first one I'm going to consider is the Laplace transform of t times sine of kt. First, let me remind you what the Laplace transform of just k times t was, which is k divided by s squared plus k squared. We've seen that earlier in the series. So then, the effect of multiplying by t, as in taking the Laplace transform with t times sine of kt, is that, well, there's a minus sign, and then there's a derivative of the result that I previously had. So in other words, I get this negative, the derivative of the Laplace transform of just sine of kt. We can compute that derivative, and that's just going to give us this minus 2 times sk, and then divided by the denominator squared. So this s squared plus k squared, all squared. So, in other words, the Laplace transform of t sine of kt is, well, this expression. Now, this example could have been done without this particular technique. Indeed, you could have just written down the definition of the Laplace transform for t times sine of kt. It would be an improper integral. You could have done some integration by parts. It would have been longer and messier, but you could have got it. Nevertheless, this technique makes it much simpler to compute the Laplace transform of a polynomial at t to the n, multiplied by something that you already know, like the sine of kt. Let's see a second example. In the second example, I actually want to begin with a differential equation, and it's a very famous one. This is called the Bessel equation. It is t times the second derivative plus a first derivative plus t times the function y itself, all equal to 0, and then some initial conditions. Note that while many of the differential equations in this series could have been done by other methods, this particular differential equation one, we don't know how to do it by our previous methods of, for example, constant coefficients. This is not constant coefficients. Okay, so what can we do? Well, we're going to take the Laplace transform of both sides. But before I do that, let me just remind you of how the Laplace transform of derivatives work. So the first is I'm going to just define the Laplace transform of just y to be capital Y. Then if I take the derivative, we had a formula for that. It was s times this capital Y minus y at the value of 0. And then the second derivative likewise had a formula. It was s squared times the capital Y, then minus s times the first initial value y of 0, and then minus just the y prime of 0. These formulas have been computed previously, and that's how you take the Laplace transform of derivatives. Okay, so then if I want to plug that into my formula, I'm going to get this long, messy expression. Let me explain. I'm going to first focus in on the ty double prime term. The multiplication by t at the front, when we take the Laplace transform, is going to result in, well, a negative derivative according to my formula. And then y double prime is this expression that I plugged in. The only difference is I'm going to substitute in that y of 0 is 1 and y prime of 0 is 0, and that's why I get the negative derivative with respect to s of s squared y of s minus s. Okay, let me look at the second term here. So now I'm taking the y prime term. This is now just plugging in sy of s minus y of 0, which we will evaluate as 1 given the initial condition. And then finally, we have a ty. The effect of the t is once again taking a negative derivative. And then the Laplace transform of little y of t is just big Y of s. On the right-hand side, the Laplace transform of 0 is 0, nothing to say there. Okay, cleaning up a little bit. Now I need to evaluate this derivative. So the first derivative on the s squared y of s is going to result in a product rule. So I get that result. Negative the derivative of minus s gives you a plus 1. There's no derivatives on the second bracket, so I copy it down. And there is a derivative on the third bracket, and so I have to take a capital Y prime of s. I can clean this up a bunch. There's a plus 1 and there's a minus 1. There's two different y prime terms, so I can put those together. This is just going to leave you with minus s times y of s. Minus s squared plus 1 times the derivative y prime of s equal to 0. So what do I have now? Well, it's kind of interesting. This is a differential equation in capital Y of s. This is quite different than what we've done in the past. Previously, when we were doing Laplace transforms, we applied it to a differential equation, you got an algebraic equation out of it, and then you try to solve that algebraic equation. Well, in this example, you start... But now, because of those factors of t in the original differential equation, that those t factors result in derivatives of the Laplace transform. Now we have the original differential equation, when you take the Laplace transform of it, becoming a different differential equation. In fact, I can clean it up because it's a separable differential equation and say that this is y prime of s over y of s is equal to minus s over s squared plus 1. Now, this is still helpful to us because the original differential equation was second order and we didn't know how to begin with other methods. But now, after taking the Laplace transform, yes, it still is a differential equation, a new one, but it's first order and it's separable, and so it's not as bad. Okay, let me look at that particular one in isolation. So if I want to solve this, I'm going to take the integral of both sides, a separate differential equation. On the left, that's going to give me a logarithm when I integrate it out. On the right-hand side, well, again, a logarithm. I'm going to use the substitution that u is s squared plus 1. So this looks like the derivative of u divided by u that gives me a logarithm of u. I have to adjust the constants because there's only an s on the top, not a 2s. This gives me a coefficient of minus 1/2 out the front and then a plus c. I then bring the minus 1/2 that was out the front and use my log rules to put it up in the exponent. And then I'm going to take the exponential of both sides here to get that y of s is a new constant. Additive constant turns into a new multiplicative constant when you take the exponentials. And then, well, the exponential and the logarithm cancel, so I'm just left with this s squared plus 1 to the power of minus 1/2, which I'll write in the bottom as a square root of s squared plus 1. So the point is, I started with a differential equation. I used the Laplace transform to get to an easier differential equation, and I've solved for that differential equation. Doing the inverse Laplace transform of this is actually somewhat tricky, and I'll leave it as an exercise for you to do as a bit of a bonus. The basic idea is to take this expression and expand it using the binomial series, and then to take the term-by-term inverse Laplace transform. You'll get some series solution to this, which is a little bit beyond the scope of our current course. Nevertheless, we have seen how useful it can be, at least. Nevertheless, we have a process that allows us to tackle this very interesting Bessel equation. Now, so far in this video, we talked about taking the derivative of the Laplace transform. The final thing I want to talk about is going the other way around and taking the integral of the Laplace transform. The formula is as follows. The integral from s up to infinity of your Laplace transform, capital F of some new dummy variable, sigma d sigma, is the same thing as the Laplace transform of the original function f, but instead of multiplying by a t, you're dividing out by a t. And similarly, if you divided by a larger power of t, like t squared or t cubed, the formula would work similarly. You take multiple integrals in that case. So the point is, if you know the Laplace transform of some function little f of t, then if you take the little f of t and either multiply by t's on the top or divide by t's, then the result is going to be that you take the Laplace transform of the thing you know, and either take derivatives of it or integrals of it. The proof of this is somewhat similar to the proof of the differentiation side, and again, I'll leave that as an exercise for you. The final thing I haven't talked about yet is what are the assumptions under which these two different formulas work? Well, the assumptions are actually very similar to the assumptions for when you can say Laplace transforms exist in the first place. Namely, I'm going to assume that my function little f is going to be piecewise continuous for all values of t being greater than or equal to 0. And then secondly, and this was sort of the important one, I'm going to assume that is of exponential order, which you'll recall meant that the magnitude of f was smaller than some exponential with some constant in the exponent c. And then these formulas are valid for all values of s which are greater than c. The demand of this exponential order comes about because the Laplace transform is, in its definition, an improper integral from 0 up to infinity with a negative exponential. And so for the Laplace transform to exist, that improper integral from 0 to infinity must converge. And as a result, the thing you multiply by that negative exponential can't be more than an exponential, otherwise you would fail the negative exponential that is in the definition of the Laplace transform tends to bring everything down to 0 very quickly, and that's great, unless the little f is so large that it in some sense cancels that negative exponential. So the demand that the f is of exponential order gives a constraint on how big the f could be. In practice, exponential order is and as a result, a very large class of functions are of exponential order, and so this Laplace transform method is actually very useful. Nevertheless, under these assumptions, the theorems are true.